All right, perfect. Welcome everybody. I think probably it's a time to start. And today we are happy to have Philipp Schmitt, who's going to speak on strict quantization of polynomial Poisson structures. Philipp, I give you the floor.
Okay, thank you. And thank you for having me as a speaker. And I guess thanks to all the nice talks that we had in this seminar previously. And today I'll try to also tell you something that is hopefully to interest for some of you, namely something about strict quantization of polynomial Poisson structures. Okay, most of this is actually based on joint work with Theorem Barmeier, who might also be in the audience or at least come a little later. So the plan for today, or let's just dive right into, well, if I can change, okay, that worked. So if I can change my slides, then we can dive right into the motivation that comes from physics. And I want to keep this brief because I assume that most of you are sort of familiar with this. So in classical physics, a classical physical system can usually be described by its observable algebra, which just consists of smooth functions on some Poisson manifold, and the time evolution is then just given as a Poisson bracket with the Hamiltonian. And quite similar, in quantum mechanics, we also have an observable algebra that now is usually non-commutative, and we therefore have the commutator as a non-trivial Lie bracket on there, and the time evolution of observables is then just given by basically taking commutator with now a Hamiltonian operator and rescaling this by the imaginary unit and a factor of Planck's constant. And now, well, if we try to let h bar tend to 0, this is what I want to call the classical limit and should somehow recover classical physics. And if I try to go the opposite way, so I somehow try to deform my classical observable algebra into some non-commutative algebra that describes the quantum system, that is what I would call deformation quantization. Okay, and then there's one important step in between, which would be sort of the formal deformation quantization, and is just sort of the formal part. So either the deformation problem sort of looked at formally, or in very easy words, just sort of the formal expansion or Taylor series around h bar being 0, which, well, we just axiomatize in mathematical terms and ask for the properties that such an expansion should have. So in our case, this is the definition of a formal star product, which is a product for a formal power series of these smooth functions on our Poisson manifold. And well, here T will always be a formal parameter in this talk, and h bar an actual real or complex number. Okay, and then as you might, or as I guess most of you know, the definition of a formal star product is just that we have some bilinear and associative product on these formal power series of smooth functions that, well, when we write it in the form that f star g, which is a formal power series of smooth functions, if you write this as in the form t to the r and then some operator cr of fg, then we want c0 to be the usual multiplication. The anti-symmetrized first order should be I times the Poisson bracket to sort of get the correct time evolution in the classical limit, and these operators should be bidifferential in a differential geometric context. Okay, and finally we just ask for normalization, so 1 should be the unit for the star product. Okay, and in a sense, formal deformation quantization sort of splits the problem of quantization into two parts, namely one formal and one strict part. And those two parts are basically what this talk is supposed to be about, namely starting with a polynomial Poisson structure on Rd. We want to discuss first the formal deformation quantization of it and then the strict one. Okay, and as a brief reminder, by polynomial Poisson structure, if pi is a Poisson structure, I will call it polynomial. If, well, the bivector that represents pi, which in linear coordinates I could just write as pi kl times partial derivatives, has coefficients that are polynomial. Okay, and here you see that I don't really bother with upper and lower indices, and I will just use this shorthand del xk for partial derivatives to keep things on the slides a bit smaller. Okay, so let's go right into the first part, namely formal deformation quantization. And you might say that this is essentially known since 20 years ago, or since more than 20 years ago, when Kontsevich proved his formality theorem. Namely, when we start with any Poisson structure, we can basically find a formal deformation quantization of it. And I guess many of you know this better than I do, but, well, here at least Gn, so the summation indices here are some sets of labeled graphs. And here's an example. Such a graph usually has n plus 2 vertices that are labeled by L, R, and then natural numbers from 1 up to n. And well, the d gamma I pi, those are now bidifferential operators that depend only on the graph and the Poisson structure at hand. And we basically obtain them by placing f at this left vertex, g at the right vertex, I times the Poisson structure at all the other vertices. And then, well, each vertex should have 2 outgoing edges. They become indices of this Poisson tensor, and sort of the incoming edges, they become derivatives and take derivatives of either the Poisson structure or the arguments f and g that we've placed at the left and the rightmost vertex. Okay, so the details won't be too important for this talk, and that's why I don't want to spend too much time here, but I just want to say that these graphs, they may contain cycles. As you see here on the right, we have an edge that goes from 1 to 2 and one that goes from 2 to 1. Okay, and so in this universal formula, we still have some weights. Those weights are sort of universal, not depending on the Poisson structure at all, and defined by certain integrals that I don't want to write down for you, but I guess it's fair to say that there's an interpretation in terms of quantum field theories by Cataneo and Felder, and a computation in terms of multiple theta values that was obtained more recently. But in general, these weights appear, or they are somewhat mysterious and hard to understand. And therefore, at least for the second part of our problem, namely this strict quantization part where we want to think about convergence of this formula, this is sort of complicated by the appearance of these weights in there. And at least in most cases, I would say, that go beyond the constant or linear case, the convergence is sort of unclear. It was conjectured for Kontsevich in some special cases, but I guess in general, it's not really known. And therefore, what I would like to present to you in this first part is sort of an alternative approach of a so-called combinatorial star product that can still quantize any polynomial Poisson structure on Rd, but that does not really need to, but where we don't need any weights. And so let's just sort of modify this theorem here. So we start now with a polynomial Poisson structure. We need to make a choice, and this choice will consist basically of a, well, for 2 indices, k smaller than L. For each choice of such indices, we will basically pick a polynomial, or rather a formal power series of polynomials that starts with minus I times our Poisson bivector in the lowest order, and then has some higher orders that you can pick more or less arbitrarily. So for any such choice, we will obtain a product. I denote this by star phi. The graphs that we sum over are slightly different, and the bidifferential operators are slightly different, and the weights, they cancel out of this formula. Okay, and later on, there will be a condition on the phi, or these phis need to satisfy some condition for this to really be a star product, but I'll get into that later. But that is the general structure of the combinatorial star product. It's very similar. Its description is quite similar. So the GNs are still graphs in like the Kontsevich graphs, but now without cycles. So the second example from before is not allowed anymore. And well, these d gammas, they're still bidifferential operators, or rather formal power series of bidifferential operators that are basically now obtained by placing minus phi over t, where we have before placed I pi. And there's some slight modifications, but I'll get into that later. And the most important part, there are no weights, so convergence properties will be much easier to prove using such a combinatorial star product than actually Kontsevich's formula. Okay, and now I should tell you about the actual definition of these products, and I'll try to do this on my next slide. So I'll have the general definition up here, and I'll try to give you an example right away of the computation in the bottom half of the slide. And this example will be for the log canonical Poisson structure. So that is the Poisson structure where 2 linear coordinates xl and xk will have Poisson bracket their product xk times xl if k is smaller than L. So in particular, this is a quadratic Poisson structure. And well, as I said, we need some input that is basically this formal power series of polynomials for two indices k smaller than L. And in this case, well, I just want to choose all these polynomials to be essentially a multiple of xk times xl, and it should be a multiple that starts, well, with it. So well, let's define coefficients qkl that are of the form 1 plus it plus higher orders. You'll see in a minute why, and subtract 1, then, well, these phi kl will have precisely the correct form from up here. And now to compute the star product of two terms. So I'm using multi-index notation here. I and j are multi-indices. So to compute basically x to the I star x to the j, we start by just writing xi and xj next to each other, using the usual ordering by in lexicographic way. So if we try to compute x2, x3 star this other monomial here, then we just write them next to each other using the usual ordering inside these two monomials. And now we just search for the first or for the rightmost occurrence of an index that is where of a pair where the index of the left entry is greater than the index of the right entry. And here the rightmost term would be this x3, x1 here. And now we're going to replace this just by xk, xl plus phi kl. So we're going to replace x3, x1 here by x1, x3 plus phi 1, 3. And due to the choice that I made up here, this is nothing else than q1, 3 times x1, x3. And now you might see why I chose this notation with q's, because now basically the coordinates here, x3, x1, they would, well, when you commute them, you pick up a factor of q. Okay, so this would be the first step. I record the result for you down there. Up here, I just keep track of the monomial that we now have. And now we just need to repeat the whole procedure. So we search again for the rightmost appearance of a pair where the left index is greater than the right one. We swap these two, introducing basically a factor of q2, 3, and now obtain like the element down here, q1, 3, q2, 3 times this monomial, and repeat the procedure. So swap the x2, x1 in the beginning, and arrive at a monomial that is now ordered. Okay, and in this case, this is supposed to be the result. So here we just get q1, 2, q1, 3, q2, 3 times x1, x2, x2, x3, x3. Okay, and if you're good at combinatorics, then it's not too hard to derive a general formula from this. And it will just be that x to the I star phi, x to the j is given by this expression here. Okay, before moving on, let me mention one important thing, namely that in each order of t, there are only sort of finitely many reductions needed to compute this order. So in particular, this gives you a well-defined bilinear operation, or this gives you a well-defined operation because only finitely many reductions are needed to compute each order of t. This is because phi kl, remember, starts in order of t. So if you fix a certain order like t to the n, well, basically all except for n of these swaps just result in changing the elements, and then to basically order these monomials, you just need finitely many steps. So this gives us a well-defined operation, and the interesting question is, of course, when is this associative and when does it define a star product? And there's one important theorem that is due to Severin Barmeier, so my co-author, and Zhengfang Wang. And in fact, like most of this first part that I'm talking about is due to those two, and I had nothing to do with this. So this is really their work that I'm just recalling here for you. Okay, so the following conditions are equivalent, namely that the combinatorial star product is associative. Then that it is associative, basically, if you just consider monomials of order 1. And then there will be an abstract condition that, well, you might have already seen that deformation problems are usually encoded in some kinds of DGLA. And so also here you can say that there is an element phi kl that should define a Maurer-Cartan element in some abstract complex. And I will explain to you in a second what this complex is. And I should not have said complex, I should have said L-infinity algebra. So Maurer-Cartan element in this L-infinity algebra here, and I'll explain you in a second what that is. But so for now, let me already mention two things. namely, this theorem will be very important. In our examples, we will usually want to check the second condition because this is very easy to check or compute. And for theoretical, for some theory, we usually want to use the third condition because this gives us a good hand to for example, proving the existence of these combinatorial star products. Okay, so what is this complex? What is this L-infinity algebra? And well, here I can't give you all the details. So if you've not heard about L-infinity algebras before, then I can't really tell you the definition. But then, well, it won't be important for most of the remaining talk. So just bear with me for these 1 or 2 minutes, and then they won't really appear anymore, except for one more slide. So, well, you might remember that the Hochschild complex in degree k just consists of basically this is not what was supposed to happen. So the Hochschild complex in order k just consists of k multilinear maps from the polynomials to the polynomials, and d here is its differential. And well, this is obtained as some x functor using sort of the Barret's resolution of the polynomial algebra. And since the polynomial algebra is very simple, we can also choose a different resolution, for example, a Cos-Weyl resolution, and then obtain a different complex that will be quasi-isomorphic. And this is what I've done up here. So this is the Cos-Weyl complex that comes out of the Cos-Weyl resolution, where, well, basically this Kj is really just a vector space that has as basis the subsets of 1 up to d that contain j elements. So this is really just a d over j dimensional vector space where d over j is supposed to be the binomial coefficient. And then, well, we're just looking at homomorphisms from here into the polynomials, which is basically what this phi kl is, because, well, we have 2 indices and phi kl is now a formal power series of polynomials, which, well, we get up here because we tensorize with the maximal ideal of the formal power series that is just generated by T. Okay, and now it turns out, basically because of what I said about resolutions, that these 2 complexes are quasi-isomorphic. Moreover, the first one is even a homotopy deformation retract of the second one. And so you can sort of transport the differential graded Lie algebra that the Hochschild complex has, at least when you change the degree by 1. You can take, like, you get a differential graded Lie algebra structure with a Gerstenhaber bracket. You can transport this via homotopy transfer to an L-infinity algebra structure on the first complex, also degree shifted by 1. And, well, so this has 0 differential. You can check that the bracket will be the Houghton-Nienhaus bracket of vector fields, and then this will have higher orders. Okay, and this is the L-infinity algebra that appears up here. And, well, the star product will be associative, basically if and only if this element phi defines for us a Maurer-Cartan element in this complex, in this L-infinity algebra. Okay, I mentioned before that in our practical examples, the equivalence of the first and the second bullet will be very important. And here's an example. If you study again the log canonical Poisson structure, we make the same choices as before. Then we see that if we try to compute this combinatorial star product on these monomials of length 1, then what happens is we try to swap xl, xk, we pick up a factor qkl, we need to swap xj with xl and xk, we pick up factors qjk and qjl, and we see immediately that this is the same as if we would do everything the other way around. So we get that the associativity condition is satisfied, so we get that the combinatorial star product will be associative. Okay, so, and it will be associative basically for any choice phi k, for any choice of qkl that is of this form here plus arbitrary higher orders. And now, well, let me give you a different example where you cannot just pick all higher orders to be 0, but where you actually need to pick them using some kind of caution or being a bit cautious. So the Poisson structure here is again quadratic. It has now here a constant term, but it's sort of very similar to the log canonical Poisson structure, except for this constant term here and sort of the minus sign in front of the second term. That would be a plus if you would consider the log canonical Poisson structure. Then we try to make similar choices than before. So we basically try to choose phi12 to be q minus 1 times x12. We need to accommodate for this extra 1 by introducing this p minus 1 here. We take similar choices than before for phi13, where now we take r minus 1 times x1, x3, and for phi23, we have s minus 1. Due to this one sign here, r needs to be of the form 1 minus it instead of 1 plus it, and then higher orders. Okay, and now if we just check what the associativity condition on monomials of length 1 gives us, well, we see that we can try to compute this term, swap x2 and x1, which gives us a factor of q, and here some extra factor, extra summand of p minus 1. Then next we need to swap x3 with x1 and x2, which gives us again factors of s and r. So the result will be qrs times x1, x2, x3 plus p minus 1 times x3. And well, if we try to compute this the other way around, we would first get our factors of s and r when we need to commute x1 past the x3 here, so that x1 is in the middle. Then we get rs times x2, x1, x3. We still need to commute x1 past x2, which gives us another factor of q, and then this additional summand of p minus 1, but now multiplied by rs. So what we obtain here is almost the same result, but with the second summand multiplied by rs in addition. And so we see that in order for the associativity condition to be satisfied in this case, we just need to pick r as the inverse of s, and we see that star phi will be associative if and only if we take this choice. So in particular, either r or s must have higher orders here, and we cannot just cut it off sort of after the first term that encodes the Poisson structure. Okay, next, what I would like to do is I would like to show you that every polynomial Poisson structure can actually be quantized by one of these combinatorial star products. So basically, whenever we start with a polynomial Poisson structure on Rd, there exist these coefficients phi kl of this form, so in lowest order starting with minus I times pi kl, such that the combinatorial star product will be associative. And the way to do this is to use the abstract characterization in the associativity theorem that I've showed you before. So to use the characterization that basically the star product is associative if and only if phi defines a Maurer-Cartan element in this L-infinity algebra here. And if you remember what it means for pi to be a Poisson structure, this just means that the Houghton-Nienhaus bracket of pi with itself is 0, or in other words, that I pi t defines a Maurer-Cartan element in this case, differential graded Lie algebra, or just Lie algebra because the differential is 0. So without like the higher order brackets. So in particular, what this sort of means is in order to find one of these combinatorial star products, we need to modify the Maurer-Cartan element that comes out of the Poisson structure by adding higher orders so that it is still a Maurer-Cartan element in the L-infinity algebra where we have these higher brackets appearing. Okay, and if you remember the Kontsevich theorem, then there's a very easy way to, using the theorem, there's a very easy way to prove this, because it tells us basically that any Poisson structure can be quantized. So there's a Maurer-Cartan element in the Hochschild cochain complex of the form I pi t plus higher orders. And well, this complex was just quasi-isomorphic to K. So applying this quasi-isomorphism, we will obtain the element phi that we were searching for. So what I want to mention here is that we are really using the Kontsevich theorem at this point. So this does not give us an independent proof of the existence of quantizations of polynomial Poisson structures, because like Kontsevich sort of enters here in the argument. Okay, so what have we done so far? We've seen that any polynomial Poisson structure can now be quantized by one of these combinatorial star products that is at least associative. And well, for now only defined on polynomials. So I should still tell you about that this can be extended to all the smooth functions, or in other words, that it's given by differential operators, because if it's given by differential operators, then you can automatically extend it to all smooth functions by just, well, applying these differential operators to smooth functions instead of polynomials. And this is the remaining thing that I want to give you a glimpse about on the next slide. It is unfortunately maybe a bit too complicated to do this in detail, but I at least want to give you some idea about why one of these combinatorial star products is really, why these combinatorial star products are really bidifferential, in the sense that all the appearing operators are bidifferential operators. Okay, and to do so, let's look at an example again. Let's take some monomial here written in blue and one in green, and let's say we want to compute like the combinatorial star product, but now we don't want to compute like the whole combinatorial star product. We just want to compute the certain contributions to it that will be encoded by a graph like the one here to the left. And how is this supposed to work? So what do we want to encode by a picture like the one on the left? Well, basically the bottom line should contain should consist of the two monomials that we want to compute the star product of. And the first line should be the first reduction. The second line here should sort of encode the second reduction, and so on and so forth. So the first reduction has two incoming arrows that meet like the bottom line, like the second element and the third element of the second monomial, so x5 and x2 here. And so this graph is supposed to encode like the process of commuting or performing all the rightmost reductions just by swapping elements until we arrive at the reduction of x5 and x2. So that would be the monomial that we obtain here. And then when commuting x5 past x2, we actually use the special element phi 2, 5. So we replace x5, x2 by x8, x8, x9. Okay, and then basically we try to repeat this process. So we look at the second reduction, which would have as an input here the third element of the first monomial and sort of the third element of the phi that we inserted there. So that would be x6 and x9. And well, again, we would perform rightmost reductions, just swapping elements until these two are next to each other, which here is easy because we just need to swap x3 and x6. We arrive at this expression. So we just need to swap x9 and x3 here. So we arrive at this expression. And then, well, we again insert phi 6, 9. So we get this monomial. And since there are no further lines here in this diagram, all the remaining reductions will again just be swaps. So what we arrive at is this monomial here. And of course, this is only one summand of the combinatorial star product, which you would obtain now if you sort of take the graphs of all possible ways to stack these boxes on top of each other, and you basically sum the contributions of all of these graphs. Okay, and well, what I want to do now, I want to simplify my life a little bit. Instead of all these boxes, I will just draw straight lines, and I will just keep the arrows as before. So by that, I just mean, well, I need to sum over all these graphs anyway, so I need to sum over all positions where these arrows hit the boxes anyway. So I will just remember the arrows and forget about the precise positioning, but I will try to remember the relative positioning. So I will remember here that this arrow is left of this incoming arrow. Okay, and then finally, I can also redraw this a little bit. I can just like attach labels to my two arrows. So basically, I want to attach the label R to the element that was like to the right. So here this would be x6. x6 was the one that came from here. So this element has the arrow tip, and well, then here the corresponding edge will have the label R. And in this way, I obtain sort of a Kontsevich graph with one additional property, namely with an ordering on the incoming edges. So for each vertex, like L here, I remember which one is the left, the right, or rather I remember a complete ordering of the incoming edges.
So in the middle graph and the left graph, not all the edges have arrows, but the right graph, all the edges have arrows. What is the significance of that?
Yeah, essentially, it's just that I wanted to make a Kontsevich graph out of the graph to the left. And so I just wanted to label the thing that had an arrow here with right and the thing that does not have an arrow with left. So basically just this edge without an arrow just became an arrow that's labeled left, and the edge with an arrowhead became an arrow that's labeled right.
Okay, so that's the rule.
So that's just sort of to translate between a picture that looks like this and sort of a Kontsevich graph with an ordering on the incoming edges. Okay, and then the claim is that okay, so that was just about the recording. So what I claim now is that the combinatorial star product is bidifferential, and that, well, basically I can give an explicit formula for it that is again of the form t to the n times some sum over graphs. These graphs now consist of pairs of a Kontsevich graph, which does not contain any cycles anymore, because, well, basically by definition, all our arrows need to point from vertices with a label I to a vertex that's labeled by something that is smaller than I. So there are no cycles. And in addition, we remember the ordering on the incoming edges. And if you now go and check what the corresponding bidifferential operator is, well, basically for each of these arrows, you would remove the element where this starts and ends, and you would insert a phi. So this basically gives you precisely this bidifferential operator that you obtain by placing phi or minus phi over t at these vertices and making the edges into derivatives. You just need to take care of two things. Namely, we remember the incoming edges. So the leftmost edge should hit sort of the leftmost element, and the rightmost incoming edge the rightmost element, which means that we need combinatorial factors in front of these partial derivatives. And then, well, if we just put up a random graph, it could happen that there are no reductions that really correspond to this graph. And in this case, we do not want to include the corresponding indices in the sum. So remember, we labeled basically these edges by indices and then summed over all possible indices. And now I just want to sum over compatible indices for which these reductions actually happen. Because, well, for example, the leftmost element is always greater than the rightmost one. Okay, and in this way, we can actually prove that we have sort of a graph calculus for the star product, that it is bidifferential and therefore also extends to all smooth functions and gives us, well, a well-defined formal star product whenever phi satisfies the associativity condition. Okay, so with that, I want to make one more remark also concerning the physical interpretation in the end, because, well, to distinguish our physical observables, those are usually the emission or the self-adjoint observables. So we need a star involution, and, well, compatibility of a product with a star involution usually means, like, if we take the star involution of the product, we sort of swap the two factors and apply the involution to them. So it turns out that this combinatorial star product is not compatible with the complex conjugation, in the sense, well, you just compute x1 star phi x2, you do not need to swap anything. So the result is just x1, x2. Whereas if you compute x2 star phi x1, you would pick up this factor of q, and q starts in first order somewhere, or has the Poisson structure sitting in first order. So those two expressions will not be the same, and they will also not just be the complex conjugate of each other. So it turns out that there is a way to understand this. And maybe one nice description is that you can also understand the combinatorial star product by, well, you take the free algebra generated by your coordinate functions, take formal power series, and now you divide out the ideal that is generated by xlxk minus xkxl minus the phi kls. So this is essentially exactly what corresponds to swapping xlxk, because you're replacing xlxk by xkxl plus phi kl. Okay, and then the statement is that if the associativity condition is satisfied, basically this algebra is just a formal deformation of the polynomial algebra, in the sense that, well, if you take formal power series of polynomials, you can find an isomorphism into A, where, well, you just take a monomial and you sort of map this to the ordered monomial in A, or rather the equivalence class of this ordered monomial here, and you extend this bilinearly over formal power series. And then, well, the way to compute the star product of f and g would just be, well, map f and g into A, compute the product there, and basically go back with the row inverse. And the conceptual reason now why the star product fails to be compatible with the star involution is that rho is not compatible with the involutions that you have. So if you neglect the ideal here for the moment, then then the free algebra will have an involution. And if you view this as a map into the free algebra for now, then, well, rho will not be a star homomorphism, so it won't commute with the involution. And, well, basically there are two ways to fix this that I just want to tell you about very, very briefly. One is, well, we could just, instead of rho, use a symmetrized map. Then this map will be compatible with the involution. So we just symmetrize our polynomials here instead of ordering them, and define a symmetrized version of the combinatorial star product just by using the sigma map instead of the rho map. And there's another way to fix this, which would be to sort of change the involution and just say that xj star should be xd minus j. And, well, this looks very weird on first sight, but if you think of your coordinates as basically complex coordinates, and you put like the complex conjugate of a complex coordinate first, and then last the complex coordinate without the conjugate, then, well, you will see that having such an involution just corresponds to using these complex coordinates, and potentially, if you have an odd number, one real coordinate in between. And then, well, if you would use this involution, again, you can check that rho would become compatible with the involutions, and then the star product becomes compatible if the ideal that you divide out here is a star ideal. And this is a condition that you can very easily check, and that in natural examples just boils down to phi being real. For example, when you take the complex log canonical Poisson structure, basically in these coordinates now, just defined the very same way as before, then the corresponding combinatorial star product would be compatible if the QKL, so your coefficients, are real. But I really don't want to spend too much time on these products because they won't be relevant for the rest of the talk. I just want to mention that they exist and finish basically the first part by giving you two easy examples. Namely, if you take a constant Poisson structure, then you can just take as your phi's the Poisson bivector in the lowest order, and you don't need any higher orders. You don't need to modify this by higher orders. You can check the associativity condition is easily satisfied. And, well, the star product that you obtain in this way is well known to all of you, because this is basically just some, so the star phi would be some sort of standard ordered star product, and the star phi twiddle is just the usual Weyl product or the Kontsevich star product that quantizes a constant Poisson structure. And similarly, you can also look at linear Poisson structures. Remember, so my Lie algebra here is always finite dimensional. So G is a finite dimensional, G is a finite dimensional vector space, and it has a Lie algebra structure if and only if the dual has a linear Poisson structure. And the Poisson structure would basically just come by, well, interpreting the elements of your Lie algebra as linear functions on the dual, and then, well, the Lie bracket of these two Lie algebra elements is the same as the Poisson bracket of these linear functions on the dual. And in this case, well, we can again just use the usual, just use the Poisson bivector in the first order, and we do not need to modify this, then we see that if we consider this algebra that I had on the slide talking about involutions, this free algebra, the ideal that we quotient out is xl(xk) minus xk(xl) plus I times the commutator of xk(xl) times the formal parameter. And this is in some sense just the version of the universal enveloping algebra of our Lie algebra, where we've sort of rescaled our Poisson bracket by a factor of it. And then, well, if you know about the definition of the good star product, you will see immediately that the symmetrized combinatorial star product is just a good star product, because the map sigma is the symmetrization map now from the symmetric tensors into this universal enveloping Lie algebra, into this universal enveloping algebra of the Lie algebra G. And well, the non-symmetrized version of the combinatorial star product, this sort of coincides with an ordered good product, if you want it that way, where you're sort of identifying symmetric elements with elements in the universal enveloping algebra by just ordering them. And in general, the Kontsevich star product will be different, and well, it is also supposed to be more complicated, so in a sense, this makes sense. Okay, and with that, I sort of want to finish this first part on the formal deformation quantization, and I just want to give you a few ideas about how you can actually prove that for many Poisson structures, these combinatorial star products that I just told you about, that they're convergent in some precise sense. Okay, so here is our general idea. And this is an approach that was sort of invented by Svea Beiser and Stefan Waldmann, that we start with a formal star product on a Poisson manifold M. For example, take the usual Weyl product on Rd. And then we try to find some subalgebra where the power series defining our product, they're in the best case finite, or maybe in a not as nice case, at least convergent in some nice sense, which here would be our polynomials, because, well, if we fix two polynomials and we try to compute the formal star product, if we try to apply higher and higher, or if we try to apply bidifferential operators of higher and higher order, well, then we just get 0. So on polynomials, basically our formal power series will be finite series in this case, and therefore we can just evaluate the formal parameter to any complex number, and we get a product on polynomials on Rd, or rather for each complex value of hbar, we get a product, so we really get a family of products parameterized by a complex number. Okay, so those products are now defined only on polynomials, and for several reasons it's nice to sort of try to find a few more observables than just polynomials. So we would like to complete this algebra with respect to some locally convex topology that is defined by certain semi-norms. I'll explain them on the next slide, and then extend the product to the completion. And usually finding this topology and showing that the product is continuous is the hardest part here. Okay, let me make one remark, namely that in this approach, this polynomial algebra typically contains some sort of unbounded elements, for example, elements satisfying canonical commutation relations that, well, with respect to the star product here, the commutator of two elements is just I times the unit. And well, it is well known that in this case, there cannot exist any non-trivial submultiplicative semi-norms that make this product continuous. So in order to find a topology here that makes this product continuous, you necessarily need to go to the locally, so you necessarily need to consider a system of semi-norms where you estimate one semi-norm by another semi-norm. So you need locally convex spaces, locally convex algebras, and you cannot just do this with normed algebras. And so in particular, if you know about C-star algebraic quantization, for example, in the sense of Riefe, then this is sort of a very, very different approach here. In this case, you really get a C-star algebra, and you should think of these this algebra P rather as some kind of multipliers or elements that are affiliated to the C-star algebra, but that cannot be inside because, well, these elements of P are, as I said, typically unbounded. So this is really sort of a different approach. And well, nevertheless, the nice thing is that the completion can have good properties. For example, it can be nuclear, and it may contain interesting observables that you might want in order to do physics. So for example, in the best case, a time evolution operator so could be contained in this completion. And therefore, well, you try to see, or you try to enlarge your algebra of observables from polynomials to these more interesting ones. Okay, and let me now give you the result of this completion of this procedure for the Weyl star product and quantizing a constant Poisson structure, and basically for the good star product quantizing a linear Poisson structure. And so we start with the Weyl product, and the idea is that sort of it stays well defined, now not on polynomials, but basically on more general series if the coefficients of the series decay fast enough. So this condition is somehow, of course, required, because if you think about what happens if you take now, say, two arbitrary series here, then to the 0th order of the product, you will get contributions from higher and higher up in a sense. So you will get an infinite sum, and you somehow need to make this infinite sum convergent. And well, for this to happen, one condition would be that your infinite sum or the series here has coefficients that decay fast enough such that, well, all these contributions stay summable. Okay, and for the good star product, you can actually find a very similar condition. This stays well defined sort of on now series if these coefficients decay again faster than c to the minus j times now j factorial to the minus 1 instead of j factorial to the minus 1/2. And I guess for this reason, people introduced the TR topology, which, well, I fix a constant r greater equals 0, and then I will just define a topology on the polynomials on Rd, basically by using the following semi-norms. So aj xj is here a polynomial, again using multi-index notation, where, well, we take the absolute value of our coefficients aj, then we take our constant that we've picked, raise this to some power that is given by the length of the multi-index, so j1 plus j2 and so on up to jd, and multiply this by the length of this multi-index factorial to some power r. And, well, in the end, what we need to do, we need to take all these semi-norms for all possible values of c that are greater than 0. Okay, so this defines for us a family of semi-norms. And now we can, well, look at the completion with respect to this family of semi-norms, and we will see that the completion basically exists, that the completion consists precisely of those series where the coefficients decay, well, as given in the theorem up here. So in other words, the theorem can be formalized by just saying that for the first part, the product is continuous with respect to the T1 half topology, and for the second part, that the product is continuous with respect to the T1 topology. Okay, I should mention here that if you look at these semi-norms, the bigger R is, the bigger the semi-norms become. So in particular, the smaller the completion is. So the bigger the coefficient R here, the fewer observables you have in the completion. So I guess that this result here for T1 half is better than this result for T1 in the sense that you find more observables in the completion or of this Weyl algebra up here than you find in the completion of the good star product algebra. Okay, and in one case, namely if R is 0, you have a very nice interpretation of the completion that you actually get, because, well, the completion would consist of series that decay faster than c to the minus j, basically for every constant c greater 0. And if you remember the Cauchy estimates from complex analysis, that basically just means that the aj are coefficients of an entire function on Ct. So in other words, the completion of the T0 topology would consist of all holomorphic functions on CD restricted to RD. Okay, and in particular, in both these examples, the topology is independent of hbar, which will not be the case for the quantizations that I will show you on the next slide. Okay, so basically what I wanted to advocate for in this talk is that using the combinatorial star product, the convergence and continuity properties of many star products can often be established due to the very simple, or to the relatively simple formula defining these combinatorial star products in our examples. And therefore, this gives us a machinery to sort of construct strict deformation quantizations of many polynomial Poisson structures. And one example here, if we go back to the easiest case of the log canonical Poisson structure from before, now taking phi KL just to be Q times XK times XL. So I've set all QKL just to one variable Q to keep the notation a bit simpler. Then we see that the star product of Xi and Xj is just of this form. And you can immediately see that basically if the formal power series here that you choose for Q converges, say in some open disk around the origin in the complex plane, I will denote this by dr, then well, I can just plug in, or I can just use this value that the series basically converges to as Q of H bar. This is now a complex value. And well, I can define a product by just using Q of H bar instead of like using the value that this formal series converges to instead of the formal series itself. And then it's very easy to show that this is still associative and therefore defines us a family of products on the polynomials. And well, in this case, if you use the TR topologies, you will see very easily that if Q of H bar is an absolute value smaller or equal than 1, then this star product is continuous with respect to the T0 topology and therefore extends to sort of all possible restrictions of holomorphic functions on CD. Okay, how does this work? Well, the proof is essentially trivial. You just plug in the semi-norms that we had before. You compute the star product using the formula from up here. You see that Q of H bar is an absolute value smaller than 1, so you can just drop it. And you just see that what you get out is the two semi-norms that you started with. So in this case, the semi-norm is even locally multiplicatively convex. And therefore, well, this gives you a very nice result that is really different from the constant and linear case because, well, the topology here is locally multiplicatively convex, but it depends very much on the value of H bar because this condition here that Q of H bar an absolute value smaller or equal than 1 is only satisfied if H bar has non-negative imaginary value. In the example of Q of H just being the exponential of IH bar. Okay, I want to say one more thing here that basically in this case, for this quadratic Poisson structure, because this is purely quadratic, things are, or the product can also be extended even to all formal power series, so to a family of products on formal power series in these variables x1 up to xd, which is sort of due to the fact that because the Poisson structure is quadratic, you don't have this, you only have finitely many contributions to a certain order because, well, the product is sort of homogeneous with respect to the orders. So there's no order where you would get infinitely many terms. So you can extend this also to all formal power series in the coordinates x1 up to xd. Okay, and basically to finish this talk, I want to show you one more example that is also sort of the maybe most interesting example, namely a quantum Weyl algebra, where we take our log canonical Poisson structure from before, we take our constant Poisson structure del y wedge dx times 1, but now we modify this basically by a quadratic term that is of the form lambda xy, where lambda is just some constant that has any positive value. And then, well, we try to pick our phi 1, 2, similar to before, as this expression, and assume that Q is just e to the I lambda t. And then we can just basically run all the machinery that I tried to present to you in the first parts of this talk. We get some algebra. I claim this is isomorphic to the quantum Weyl algebra just by the construction that I showed to you. So this is the free algebra in two variables, then taking formal power series and then quotienting out the ideal generated by yx minus qxy minus it. I can evaluate basically for all possible values of hbar. I can evaluate my formal parameter to hbar and obtain a product on polynomials. This is just, well, if you start with two polynomials, you write down a formula for this product, you see that phi will only appear like basically finite, or you only need finitely many reductions. So this Q here, there will only appear polynomial in Q or so, and this will always be convergent just because, well, this formal power series here converges for all possible values of hbar. So whenever I fix two polynomials, my product will converge for all possible values of hbar. And better yet, it will be continuous with respect to the T0 topology, so extend from all the polynomials to, well, the restrictions of the entire functions that I showed you before. And well, for this to be the case, there was some condition on the previous slide already that the absolute value of Q needs to be smaller or equal than 1. This is what we still need, and therefore sort of we need to restrict to all values of hbar that have imaginary value greater or equal than 1. And we also need that the Q here does not become 1, so we sort of need to exclude like multiples of 2 pi over lambda. Okay, and then finally, we can sort of take two limits or consider the classical limit. What the classical limit would mean is we fix two functions in the completion and then look at the map that sends hbar to the star product of these two functions, or to basically the commutator divided by ihbar and well extended to 0 by using the usual Poisson bracket of f and g. And then we see that these functions are continuous on H and even holomorphic in the interior. Okay, and now I think I have 1 minute left. And in this 1 minute, I just want to tell you that this result is much nicer than for lambda equals 0, where the star product is continuous only in the T1/2 topology. So the completion is way smaller. And I want to give you the idea of the proof, which just consists in you compute what happens when you take the star product of y and x to the m, for which you need to, well, commute these variables past each other, introducing these additional factors. What you see is, if you perform this computation, basically you get like a series here, 1 plus q of h plus q of h squared, and so on. If q of h was just 1, then this would just be m, and this would basically grow with the order m here. But in this case, if q is not equal to 1, we can rewrite this just as 1 minus q of h bar to the m divided by 1 minus q of h bar. And the nice thing is now, well, we assumed that q of h bar has absolute value smaller or equal than 1. So the whole numerator here has absolute value smaller or equal than 2 for all m. And the denominator, well, this is somehow bounded, or the inverse of this is bounded because q of h bar is a fixed constant that might be somewhere close to 1. But so the point is that the bound on this first coefficient does not depend on m anymore, but is sort of a fixed constant. And because this is a constant, you can now just compute what the star product of arbitrary monomials is. You see this is basically a sum of 2k terms, each bounded by this sort of constant to some power k. And these constants you can just absorb in your continuity estimates. And this is the reason why the combinatorial star product in a way behaves here, or why this quantum Weyl algebra behaves much nicer when it comes to convergence than the original Weyl product. Okay, and finally, I actually wanted to give you a brief outlook of what we've done or not done yet. So similar results you can obtain for other quadratic Poisson structures, and the best results you obtain only when you choose your phi properly, because then you can achieve the biggest completions. Okay, but I think my time is over, so I won't discuss all this in detail. And finally, I will just give you a few references of the main articles that I sort of cite or reference during my talk. Yep, thanks for your attention.
Thanks a lot. All right, questions or comments? You can either unmute yourself or raise your electronic hand. Ellie?
I have a question.
So in that last big example, there's a hyperbola where the Poisson structure vanishes. So does that survive as an ideal in your quantized algebra?
Sorry, you mean this example here?
Yes.
That is a good question. I didn't think about this yet, whether you see this in the quantized algebra as an ideal. I honestly don't know.
Mikola?
Hi, can you hear me?
Yes.
Okay, so I have a question about the first part of the talk where you presented this product, formula for the star product that depended on phi or phi.
Yeah.
Right, so you have this formula that depends on this phi, and you say that it always exists, but how do you, and sorry if you said it already, but how do you find it in concrete examples? Do you have some general algorithm, or it's kind of case-by-case analysis?
Yeah, this is a very good question. Like the existence proof, as I showed you, sort of depended on the Kontsevich formality, so you don't really want to use this in a concrete example. And then, well, in the examples that I try to show you here, you can just, well, basically compute or try to compute this associativity condition for monomials. And usually this is pretty much, or usually this is not too hard. And usually this tells you immediately how you need to choose your phi. For example, in this case, in this example down here, just needed to choose your phi using that R is sort of the inverse of S. So basically, to go back, if you're given a concrete example, what you want to do is you want to use the equivalence of the associativity of the star product with the second condition, and you just write out the second condition, making a general ansatz for the phi, and then usually, like at least in more or less all the examples that we looked at, this gives you a very easy equation that you can, this gives you a very easy condition for the phi that you can just demand for. But okay, I don't have a general algorithm that would guarantee sort of that, or that can handle all, or I don't have a proof that there's an algorithm that can handle all these examples apart from the one that uses Kontsevich formality.
Thank you.
Does this answer your question?
Yes, yes, it does. Thank you very much.
More questions or comments? I possibly have a question related to Mikola's question. I have a vague memory, but not a very precise one, that there was a work or maybe several works about, like, basically you in this approach, right, to deformation quantization, one is trying to define the deformed algebra by generators and relations. Right, yes. So the generators are those xi's, and the relations are defined basically with the use of those phi's.
Yeah.
And okay, so I like one question is, I think in the Kontsevich approach. Maybe Alberto Cattaneo with some collaborators, but I don't quite remember. Discussed that question. What would happen if one tries to define the Kontsevich deformation quantization algebra by generators, let's say on RD, generators being similar to this approach, xi's, and then what will be relations? So I don't know whether you looked at it. That would be one question. And the other question, when you define an associative algebra by generators and relations, and suppose you don't want it to be formal, right? You want the relations where the deformation parameter will be a complex number. I think there would be some question of PBW. Is it true that your algebra in the end have the same size? Or maybe it has a smaller size because there would be some whatever collapses because of relations. So what is known about this PBW question?
Okay, let's maybe start with this PBW question. And in a sense, what I had on at least if this associativity condition is satisfied, like formally, this is exactly what guarantees you that when you do these relations or when you do these swaps and you quotient this out, that you don't get something, that you don't get like unwanted relations, but you only get the ones that you really want, so that this quotient is really sort of this isomorphic to polynomials on RD and then formal power series.
Sorry, that I understand, but then later on, right, when you discuss the strict deformation quantization, you plan to put this parameter equal to a number.
Oh yeah, okay.
Then what?
I guess in many cases there, I didn't really discuss this in detail. What happens is that if you compute like xi star h bar xj, and you compute a formula for this, where basically the q appears like only polynomially, and you know that the q already converges as a formal power series on C, then also these polynomials of q, because they're sort of very easy functions, they will also converge on the same disk.
But you're saying basically we need to redo it case by case.
Well, I would say that at least the associativity then comes out immediately, because you sort of can get convergence of all the different ways because like, how should I say this? Evaluating the formal power series sort of commutes with taking the product. So it doesn't matter whether you first would take the formal star product and then you would like evaluate your formal power series, or whether you would first evaluate your formal power series and then would try to.
Okay, I don't know. I'm not 100% convinced, but also maybe you're right. I don't know.
Well, okay, at least what I wanted to say is that if you have this actual convergence, you can get the associativity of this strict product sort of out of the associativity of the formal product. Okay. If you pay attention to the details. Of course, this does not immediately answer your question if you think about relations and try to replace the formal parameter in these relations by.
Okay. I think maybe maybe we can ask Brent later on, because he put some comment on the chat. But maybe now should give
this diamond lemma comment. This refers to basically the reduction system or so that you're mentioning in the sort of formal case, I think.
Okay.
So I should have maybe said this. I only presented this construction for you for polynomials on RD. But like Severin Barmeier and Zhengfang Wang, they actually did this they did this for basically path algebras of quivers modulo some relations. And then there this diamond lemma comes in, and this diamond lemma is essentially what sort of guarantees you this associativity theorem that I showed you in the beginning, that, well, that these properties are equivalent, or in other words, that it does not matter in which order you do the reductions and you always get the same result.
Okay, thanks. Maybe we, whatever, there are further comments, maybe we get back to it
Yeah.
in a moment, but so Kevin.
Right, thank you. So thank you for a nice talk. So I had a question related to the first part of the talk. So this infinity algebra that you mentioned, whose Moore-Cartan element can be quantized by a combinatorial formula. Is it the same as a shortcut infinity algebra, which was introduced in the context of infinite dimensional Poisson manifold?
To be honest, I don't know. Maybe Severin knows, but I can't say immediately.
Because I remember there was this paper. Sorry, yeah, there was this paper by Merkulov and Pfeffer which performed this two-step quantization, and I think the intermediary step was this shortcut infinity algebra, whose Moore-Cartan element was what they call quantizable Poisson manifold. And right,
I think we use a different homotopy, so it's not on the nose the same thing. But yeah, it's of course very closely related. Being
I see.
quasi
because in their case, I think there was an explicit formula in order for any Poisson bracket to obtain a quantizable Poisson bracket from it. So yeah, okay, thank you.
Okay, thank you. Ellie?
So another quadratic example. So the Polish standard sphere is a non-commutative deformation of the two-sphere, which has one classical point. And if you obtain the Poisson structure corresponding to that, you get a Poisson structure in the two-sphere that vanishes at one point. If you remove that one point and conformally project to the plane, then in standard coordinates, the Poisson bracket is such that Poisson bracket of x with y is 1 plus x squared plus y squared. So it's a fairly simple quadratic one. I'm wondering whether you've looked at that example, and if not, I'm suggesting that you look at that example and compare it to the Polish sphere.
Yes, I would say that is a very good suggestion. We've not looked at this precise example. I think this looks very similar to sort of the star products that you get of Wick type that you get out if you use one of these complex, if you use sort of this complex log canonical Poisson structure, but I would need to check, and I would be fairly confident with our methods you can sort of extend this to some nice class of functions, at least on the plane then. And then of course the question is what these functions might correspond to when you try to move this back to the sphere. So I can't give you the answer right away, but I'm fairly confident with the methods that I try to present you here. You can apply these to this case and you will get some result and some extension to bigger algebras.
You know, I think it might be interesting to compare with the fairly simple description in terms of generators and relations for the Polish sphere.
Yeah, definitely. I think that is a very good suggestion. We should definitely look into that.
Thanks.
Okay, thank you. Any other questions? I don't know, Severin, do you want to say something about your comment on the chat, or?
I just basically what Brent Pim put in the chat was also what my comment was about. Basically, that even after evaluating the formal parameter to a constant, you have the same C basis as a vector space. So the algebra does not get smaller if you evaluate, and also not in the formal case. Yeah. That was about your question.
Oh, but why not? Why it can't happen that somehow when you evaluate, who knows, maybe some basis elements, whatever, become the same or whatever, why not?
Yeah, but the K basis is still given by monomials which are ordered in increasing order.
But then we assume something about the relation.
But between those, there's no relation, because the star product is sort of ordered in such a way that once you are in sort of standard form of the monomial, there's no more reductions you can do, and yeah, this implies.
Oh, okay. Okay, now I got it.
Okay.
So if you're doing star algebras and then you wanted a C-star algebra in the end, you might get additional relations popping up because they would not give you nice operators. So that's a way in which things could shrink.
Yes, and well, C-star algebras are particularly problematic in this approach because, well, our elements are not sort of bounded, but even, yeah, this is also one of the questions that I wanted to mention in the end. Like if you do the star algebraic approach, so if you use one of these Wick products, if you complete this and so on, you can ask what are the positive linear functionals, because those would give you a GNS construction and ways to represent things on a pre-Hilbert space or on a Hilbert space in the end. And well, it might happen that sort of the C-star enveloping hull or so of your star algebra is just 0 or so, because it does not allow any nice representations. And understanding this, well, would be a project of its own.
Right, thank you. Further questions or comments? Well, if not, Philipp, thanks again.
Thanks.
Well, thank you very much, everybody. And so we'll return on global Poisson in 2 weeks from now. Well, thank you and bye.
Yeah.